This is an A12Z based Apple Developer Transition Kit. Now, in this video, what I intend to do is I intend to get this Developer Transition Kit back up to fully functional condition. Now, for those of you who don't know what the Developer Transition Kit, or DTK, is, essentially back in 2020, during WWDC, when Apple announced their transition from Intel to Apple Silicon in their Macs, they offered this device to registered developers to basically rent and use it to port or develop software for the new Apple Silicon platform. So as I mentioned, this machine is an A12Z based system. You can see the A12Z SoC right here, and basically at its very core what this is, it's an A12Z iPad Pro put onto a Mac Mini logic board. That's the easiest way to describe it, and I think that's the most accurate way to describe it. So for those of you who know about the Developer Transition Kit, you would know that, well, all of these devices were supposed to have been sent to Apple developers for a period of about 6 months or so, and then at the end of that period, they were all supposed to be sent back to Apple from the developers that actually got them for that program. Now, they initially cost $500 to get this device from Apple, just to borrow basically for the 6-month period. And when they were returned, Apple provided those developers a $500 rebate, or I guess in-store credit that they could use towards the purchase of another Mac. Now, with that all said, you're probably wondering how the heck I even have this device, or at least have the board of one of those devices. Well, the story about this one is, basically, this device, along with quite a few other of these, were actually already sent back to Apple. However, this one and all the others that were sent back to Apple were sent from Apple to China for recycling. So basically, when Apple receives any device, whether it's an iPhone you give to them for recycling, something they buy back from you in some cases, and including any of their prototype devices that they no longer need, they basically just send them to China and have people in China do whatever they need to do, steal parts off of them, whatever, and then just basically destroy the boards. So this board really was supposed to have been destroyed. Now, with that said, just by looking at it, you might think that, well, obviously it wasn't destroyed, and that's correct, but you might think that, you know, you could just power this on, plug it in, power it on, and it would just work. Well, unfortunately, that is not the case for a couple reasons. So the main reason is the damage that was done to this board actually by Apple themselves before sending this board to China. Now, I don't know if that's the case for certain, but based on what I've seen with other prototypes and other devices that have been sent to China from Apple, this little cut here in the board was done by Apple before sending the board to China. So I guess they thought by creating this cut here, that would effectively disable the board, making it pretty much unusable. And in a sense, they were right, but in another sense, they were not correct, as we will see in just a minute here. But as you can see, the other issue with this board, and it might be a little bit more obvious than that cut, is that the two NANDs here have been removed. Now, I believe these were not removed by Apple before sending the board back to China, but these were removed by some workers in China because they like to resell these for use on other systems that may have had bad NANDs, or in order to use those NANDs to upgrade the onboard storage of other systems like T2 Max and some older iPhones is what these NANDs would also be compatible with. So with that said, in this video, we basically need to accomplish two things. We need to fix any damage caused by this cut here, and we need to install these two NAND chips here. Now, another thing you might notice if we go ahead and take a look at these two sets of NAND pads here is there's a bunch of components around them and below them, but specifically these components down here below the chips have been removed by accident, I guess, just during the process of removing these underfilled NANDs. So I guess that's to be expected. But it does, of course, create a little bit of extra work for us to do here, because we do, of course, have to populate all of these components once again to actually allow NANDs installed here to function properly. Now the short is another story. The short, while it doesn't actually damage any of the traces in this area, what it does do is short the inner layers of the board together. So basically, any layers, this is a pretty dense board, so I think it's at least 8 to 12 layers. So this cut here, as you can see, it's kind of jagged, and it kind of deforms the board where it was cut. That actually causes shorts in between the layers of the board in this area. So basically, in order to rectify this cut, we have to clear all the shorts that happen where this cut is. And by the way, one of the shorts is actually the main 12-volt rail that the power supply connects to. And if you do plug in a power supply with this shorted like this, it will damage the power supply. Don't ask me how I know that. But anyway, so of course, step one to this restoration process is of course to clear that short. And there's a few steps involved to do that. I have done this before on another one of these boards that I have, and I have figured out a pretty good method to get those shorts cleared effectively. So we'll start with the first process of doing that, which, hilariously enough, is actually widening this cut using a cutoff wheel on a Dremel. Alright, so as you can see here, I've gotten the board back out here so we can begin the process of clearing this short here. But before I do, I just want to show you what exactly the short looks like and what it does to the 12-volt rail here. So I'm going to go ahead and turn on my multimeter into continuity mode, and we're just going to probe across one of these capacitors here, which is on the main 12-volt rail from the power supply. And you can see it is a dead short. So if we were to plug in a power supply here, it would just short it out completely as soon as you gave it power. So definitely do not do that till we have verified that the short is indeed completely cleared. So with that out of the way, the first step to this process is to cut this cut wider, to make this cut wider basically. So before we do that, the first thing I want to do is kind of straighten this cut out if at all possible. Sometimes this isn't really possible, but if it is, we want to try to do that. So basically I'm just going to take my hands and kind of squeeze the cut back together as close as I can. So I can't really do it much, as you can see there, but that's okay. No big deal there really. So with that out of the way, we'll get the tools out that we need. So as I mentioned before, the first tool we're going to need is a Dremel with a cutoff wheel, as you can see I've got right here. This will only be used to make the initial rough cut, but after that point we will not need that any longer. But at that point we will then need two files. We'll need this round file, we'll need this flat file, and then we're also going to need a drill, which I've got right here. So step one, like I said, is to cut the cut and make it wider using the cutoff wheel. So I'm going to go ahead and do that now. Now after doing this a few times, I found the best way to do this is from the bottom. It can be a little hard to get the cutoff wheel in there. As you can see, the board kind of impedes the body of the Dremel here. So if I had like a right angle cutoff wheel, that would actually make it a little bit easier. But unfortunately I don't have one that's small enough to do this job. But we'll try it from here. Sometimes it can be easier to do it from the top and just kind of go like this. And when we cut this, we're going to cut almost all of the cut, not the entire cut, but most of the cut. And you'll see why here in a second. But let's just go ahead and get the Dremel started, and I'll start cutting out this cut. Alright, so that's perfect right there. You can see we haven't taken the entire cut out, but we have taken most of the cut out. So yeah, you can see there is still a little bit of the cut left, and that is exactly what we want. So let's go ahead and take a look at it from this side. Yeah, so you can see that some of the cut is still there on the top side as well, and that is perfect. That's exactly what we want. So now what we need to do, and this is going to seem a little weird and unconventional, but we're going to take the drill and put this file in the drill. You can see I've already done that, and it's kind of damaged the little grip part of it there, but that's okay. So we're going to take this and chuck it up in the drill. Get it good and tight there. So we've got our file chucked up in the drill here, and basically what we're going to do with this is we're going to run this down into this crack that we've cut out here until the crack is completely gone. So let me go ahead and do that now, and we'll also widen out the cut a little bit more with this as well. You don't want to go too crazy with it here. Okay, and that's about good there. So you just want it to be a nice and even U shape, as you can see we've got right there. As you can see, I did widen out the top a little bit as well. That's fine. So now let's get some of the dust off of it here. That doesn't cause any problems. And now if you take a close look at the cut that we've now widened even more, you can see that there is a little bit of fragmentation on both the top and the bottom. Now we're not going to worry about that fragmentation on the bottom, but on the top we do want to clear that out. And in order to do that, I'm going to use the same round file, just take it out of the drill. And I'm just going to kind of take it and kind of work these fragmentations down into the cut, just like that, and then kind of shave them out with the layers. So don't go against the layers, go with the layers like this. Just do that a little bit more, just to make sure everything's nice and clean. Okay, and that looks really good there. So you can see we've got very little fragmentation on the top here. Actually, we've got one more piece we can get rid of. Okay, it doesn't have to be perfect, but that should be good right about there. So, now with that all done, let's just put the board down. And before we do anything else, let's just check it with continuity one more time and see if our short just happens to be cleared. And as expected, it is not. That's what I expected. I just wanted to check it. You always want to check just to make sure, you know, if you don't have to file anymore, then best not to, of course. So, with that done, the next thing we need to do is get a couple alligator clips here, clip leads, connect them to the 12-volt rail. So I'm going to do that with a pigtail that I cut off of another power supply. And we're just going to take this and connect it to the multimeter probes. And as you can see, as soon as I did that, the multimeter beep is on, because of course there's continuity there because there's a short there. So basically at this point what we're going to do is we're going to use the flat file to file against the board like this, and what this will do is it'll kind of take away each layer of the board layer by layer, and also will kind of separate the layers out from the widened crack here. You'll see what I mean as we do it, but you want to do it with the multimeter connected to this at all times. We connect the multimeter, file, and just keep filing until the beep stops on the multimeter. So let me hook that back up. So now with our flat file, we're just going to start filing flat against the board. Do not go at an angle. Don't file in here like this, only flat. Okay, and as you can see, the multimeter has stopped beeping. So once you get to that point, you want to go a little bit further because you see this area right here. That can be a potential issue. So let's just file. You can see when I put the file on it, it kind of shorts again. Let's file it a little bit more just to get this smoothed out a little bit, and then we should be pretty good at that point. Okay, of course you want to get all the dust off because that, as you can see, makes a little bit of contact as well. So now at this point, we can go ahead and hook this up to my bench power supply. I'm not going to use the official power supply for this just yet, and you'll see why in just a minute here. But I'm going to hook this up to my bench power supply, test it, and see what it exactly does. Okay, as you can see there, I've gotten the bench power supply connected to the DTK logic board, of course with our filing done. So let's go ahead and look at the power supply here. Now when we turn this on, we're going to look at the current draw to determine what is going on with the board. So I'm going to turn it on, and if it doesn't look right, I'm going to turn it off pretty quickly because I don't want to leave it on too long if there is still another shorted rail in there. There are other rails that can be shorted other than just the 12 volt. But let's go ahead and turn it on and see what happens. Okay, so you can see how it went pretty high up there in the current. We do not want that. That means there is still another rail shorted. So we need to go and file some more, test again, file some more, and test again. And then once I get it to the correct point of no more shorts on those layers, I will show you what the correct current readings should be during the power on process. Okay, so after a few more iterations of filing, testing, filing, and testing, only took me about 3 times. I also did notice there was still a little bit of the crack left, so I filed that out using the file on a drill like I showed you earlier. So everything looks good now, so let's go ahead and turn it on. So you can see it started out at about 10 milliamps. Then it went to about 100 milliamps, and then it went to about 129, 130 milliamps, where it's sitting right now. And in theory, that should be the board in DFU mode. All right, as you can see here, I've gotten a computer open, and I've gotten the DTK board connected to it via the USB-C DFU port there. So let's go ahead and turn on the bench power supply with the DTK, of course, connected, and we'll see if the machine detects it in DFU mode. And there it is. Look at that. Let's go ahead over here. You can see all the info about the device. You can see this is a CPFM03 DTK, which is important because if it was a CPFM01, we could not restore production software on it, which of course we want to do in this case. So that is really good. I like what I see here. You can see Purple Sniff detected it, and of course macOS Finder detected it as an iPhone, which is kind of funny. But at this point, we're in the clear. The board is pretty much fully functional at this point. So now all we need to do is prepare the board to get some NANDs installed onto it. Alright, so as you can see here, I've gotten the board back on my workbench. So the first thing we need to do is remove all the residual underfill material on these pads here. So in order to do that, I'm just going to turn on my hot air, and we will use that to remove all the underfill. Now, this board has a lot of thermal mass, so it makes that process a little bit tricky, but we'll just go with it. I don't want to put it on a preheater because you risk knocking off these other components a lot easier, which I want to try to avoid. So we're just going to do it on the bench with only the hot air, and hopefully we should be able to get it done without much issue. Okay, so that looks pretty good right there. So the next thing we need to do is use the soldering iron, some flux, and some solder wick to remove all of the residual solder from the pads. And then the pads are pretty much ready to have some NANDs installed. Okay, so that looks really good. So now I'm going to go ahead and get a little bit of extra flux on these pads that have had their components removed. We're going to go ahead and tin those pads with, of course, some leaded solder, and that will make it a whole lot easier to install those components back onto the board. Okay, now with that done, I'm going to go ahead and clean up all the flux from the board using some rubbing alcohol and a paper towel. And that looks pretty darn good. So what I'm going to do now, and I'm going to do this off camera, I'm going to use another board. I do have quite a few of these boards that I'm going to use for parts. So you can see I've got another board right here that has most of these components already in place. You can see I can't use this one because of that drill hole right there through the SoC. So of course this board is only good for parts. So I'm going to go ahead and just remove all these components here that I need, get them all laid out, and then I'll begin the process of installing these components onto the correct pads on this board. So with that, I'm going to go ahead and get all those components removed and then prepare them to get them soldered onto this board. Alright, so as you can see here, I've got the board on the preheater this time, and I've got all the components that we need to install laid out over here next to it here. You can't really see it, but it's laid out on my workbench here. So I'm just going to go ahead and get started by simply installing all of the components that are missing. Alright, so as you can see here, I've gotten all the components installed. So if we go ahead and take a close look here, you can see what we've done here. I didn't install quite all of them, like I didn't install this capacitor because it's just a decoupling capacitor, doesn't really matter. But as you can see, I've got all these installed. I installed those two capacitors, these two resistors right here, which are important, all these, and everything looks to be installed and everything looks really good. So the next step is we need to prepare some NANDs for this board, and in fact I do have one NAND that I'm going to use that I took off of a 2020 Intel T2 based MacBook Air logic board, and that is a TSB 4227 NAND, which I've got right here. I've got this NAND right here. You can see TSB 4227. Now this NAND is used on a 256 gigabyte A12Z based iPad Pro, but this specific NAND itself, one NAND, is 128 gigs in size. So in this instance, we are going to be using just a single NAND, single 128 gigabyte NAND, and I'll explain why in a minute. But for now, I'm going to show you how to program this NAND appropriately for a DTK board like this. So let's go over to the computer where the P13 NAND programmer is hooked up, and we will program this NAND to work appropriately on this board. Alright, so as you can see here, I've got the P13 programmer out, so we're just going to take this NAND, and the only reason it's labeled 1 here is because it was NAND 1 in the system that I took it out of. It really doesn't mean anything in the context of the DTK here. So let's go ahead and just put this in the programmer. You can see it detects it as the TSB 4227 there at 128 gigs. So over on the computer here, the first thing we want to do is we want to format the NAND. So let's go ahead and do that here. Sorry. First, we want to select the device that we are formatting the NAND for. And in this case, we're formatting it for a iPad Pro, an A12Z based iPad Pro essentially. So if we go ahead and select iPad Pro 11 4th Gen, that is the A12Z based 11-inch iPad Pro, now we can select Format NAND, select that, and we'll just format the NAND like so. Alright, now what we need to do is set up the sysconfig info appropriately in order to allow the system to properly detect all of its necessary info. So like the serial number, MAC addresses, stuff like that is stored in sysconfig. So the first thing we're going to do is select restore sysconfig, and I'm going to restore it from this dump here that I made of another iPad. So as you can see, it says restore sysconfig data OK. So now what we want to do is select query info. And here's all the data from that iPad Pro that I originally dumped the sysconfig data from. So now what we need to do is we need to get the sysconfig data modified appropriately for a DTK. So I've got some serial numbers here that match a DTK. So we're going to take these serial numbers, all this info here, and just paste it into the sysconfig section here. And this can stay the same, it doesn't really matter. I guess we can just modify it anyway. And for the model number, we want to type in A2330 because that is the model number of the DTK. And let's say write selected info. So you can see it wrote all this data successfully. So now what I'm going to do is just take the NAND out, put the NAND back in, let it reload here. And let's query info again. So that's good. So you can see all the info that we put in there is still in there, which is good. But the last thing you need to be aware of here is this right here. As you can see, it says Wi-Fi is locked. So in order to fix that, if you leave this like this, it basically just won't have any Wi-Fi support, because the way these work is the Wi-Fi chip is actually serialized to the NAND. And if you put the NAND on a machine with a different Wi-Fi chip or replace the Wi-Fi chip, the Wi-Fi will stop working unless you unlock Wi-Fi. So we're just going to select PCIe unlock Wi-Fi. You can see it says Wi-Fi has been repaired, and if we query info again, you can see it now says Wi-Fi is unlocked. So that's it. We're now ready to solder this NAND onto the DTK logic board. So let's get it reballed, and then we can get it soldered onto the board. Alright, so as you can see, I've got my BGA stencil out here. You can see I've got the NAND on a piece of Kapton tape here. So we're just going to take it and apply it to the bottom of the stencil like so. Make sure it's well aligned there, as you can see. So now we're just going to take some solder paste, apply it to the pads, of course, and then we'll heat it to get balls of solder on the chip. Alright, so I got a little bit of solder paste here, so let's go ahead and spread it out. Alright, and now with the solder paste nice and spread, we'll go ahead and turn on the hot air, heat it, and get the solder paste molten onto each and every pad. Alright, so as you can see, all the solder has melted onto every pad. So now let's just go ahead and take the chip off. And now we'll just apply a little bit of extra flux to it. And then we'll heat it and melt the solder one more time. Alright, and that looks really good. So the last thing I'm going to do is clean all of the flux off of this chip. That way any little pieces of solder that are suspended in the flux will get removed. And then we can finally install it onto the board and see if we can actually restore software onto the device. Alright, so as you can see here, I've got the DTK up on the board preheater. I've got the hot air already warmed up. So the only thing left to do is solder this NAND onto the DTK logic board. So we're going to solder it to this set of pads right here, because this is NAND 0, closest to the SoC. I'll apply a good amount of flux there. Then we will take the chip with pin 1 in this lower corner here and align it to the pads. And that's pretty good right there. So now we'll just simply take the hot air, heat it, and solder it onto the board. Alright, and that looks really good right there. So that is the chip fully soldered and ready to go. Alright, so I've got the device connected. You can see right there. Of course, it is the same exact device with the cut right here that we've already fixed. Just to show you that right there. So, with that all plugged in and it connected to the computer, let's turn it on one more time and attempt to restore software onto the device. Okay, and it still boots into DFU mode. That's good. That's what I like to see. So now we'll just simply select Restore while holding down Option. We'll select the 11.2.3 IPSW, which is the latest that the DTK officially supports, and attempt to restore the device. Okay, so far that's a really good sign. And it's restoring software. Alright, so I'm just going to let it sit here. We'll wait till the restore process is done and see if we experience any errors. Hopefully not. And in theory, if all goes well and this fully restores, we'll have a fully functional developer transition kit on our hands, which is very, very exciting because I have wanted one of these for a very long time. So the fact that I have this opportunity right now and it's actually working is just insane. So let's wait here, wait for this to finish, and hopefully everything from then on out will go exactly to plan. Alright, and it looked like the restore completed successfully. So yeah, that's a really good sign. So now let's go ahead and get the board hooked up to a real Mac Mini 2018 Mac Mini power supply, keyboard, monitor, and mouse, and see if it actually boots into macOS. Alright, so you can see here I've gotten the DTK all hooked up and ready to go here. You can see I've got a speaker plugged into it here. I've also got it connected to a 2018 Mac Mini I/O shield just for the Wi-Fi. As you can see, I've got it connected to the Wi-Fi antenna connection there. And I've got the power supply, of course, connected for a 2018 Mac Mini as well. So with that, let's plug it in and see what it happens to do. And it chimed. That's a really, really good sign. Let's take a look at the screen here. And we've got video. Alright, so as you can see here, we're at the Activate Mac screen, and this is the next hurdle we have to bypass here. That's no big deal, but let me go ahead and just show you what it'll do as it is right now. So let me go ahead and connect to my Wi-Fi here. And you can see it tries to do something. It says your Mac is activated. Go ahead and restart. But as you can see, we're back to the same place again. And it'll just keep doing this over and over and over again. Now, The reason for that is because of that serial number and MAC addresses that we programmed on, because of course we don't know what the original serial numbers and MAC addresses were, because of course that's stored in sysconfig and that's stored on the NAND, and this board didn't come with any NANDs. But thanks to Apple's FDR, or Factory Data Recovery Server, we can actually query that and retrieve the original serial number and MAC addresses for this device. And in fact, the P13 programmer actually has a built-in feature that allows you to do that. So, with that said, we need to shut this down, desolder the NAND, get it back off the board, and then we need to put it back into the P13 programmer, query that FDR server for the correct serial number, program that in, and then we should be able to successfully activate the device. Alright, so as you can see here, I've got the JC P13 software open right here. So let's just go ahead and put the NAND in just like we did originally. Alright, so we'll go ahead and query info again. It should be exactly the same. As you can see, there's no changes there. So what we need to do in order to query the FDR server is we just simply select this option right here that says query code/unbind. And the reason we used that single NAND configuration in this instance is because this process only works with a single NAND. Now, once we get this data from the FDR server, the serial number and MAC addresses, then we can configure that or program that onto any configuration of NANDs we want, assuming it's a valid configuration for an A12Z based iPad. But for now, we're just going to stick with this NAND just for the purposes of this video. So we'll select fast mode here, select confirm, and then we just simply sit here and wait. And I should add that the software must be restored on the device you intend to query. So because I restored on the target device, of course, now this should be able to read the ECID and other stuff it needs off of the NAND since we just restored it, and then use that data to query the FDR server in order to get our serial number and info. So this takes a little bit of time sometimes, so we'll just sit here and wait, like I said, and hopefully it should succeed any minute now. And there it is. So we can select stop because we already did what we needed to. And let's go up here. It says the iPhone ECID with the ECID, of course, of that DTK. And there's our necessary data. So let's go ahead and paste it over here. And now all we have to do is just take that data and paste it in. It's 898A and D3, perfect. The serial number is correct, and the board serial number really doesn't matter, but that's actually printed on the board itself, luckily, so I can read that off and put that in here when I do my final config later. But for now, this is fine. Let's go ahead and write the selected info. You can see all the data has been written. Let's take the NAND out, put the NAND back in, just so it reloads it. We'll query info again. Wi-Fi is unlocked, that's important. We've got the correct serial number and the correct MAC addresses. So there we go. The NAND is now programmed appropriately with the correct serial numbers and MAC addresses for that specific DTK. So now we can put the NAND back on the logic board, test it one more time, and this time it should activate successfully. Alright, so as you can see here, I've got the DTK back on the board preheater. We're ready to solder that NAND back on. But as you can see here, I've left the solder on the board, and I've also left the solder on the pads of the chip itself as well. And because I did that, we can actually reinstall it without reballing it. So first I'm just going to apply more flux, just like so. And what I'm going to do is I'm going to put the chip on and just get it as close to the correct position as possible. So just kind of get it touching the solder balls, just like that. And then once it's like that, we can take the hot air, heat it, and it should just pop into place. As you can see, it just popped right in. So let's keep heating it just to make sure it's fully molten. And that's it. So we'll wait till the board cools down once again, plug it back in, and see if we can activate it successfully. All right, as you can see, I've got the DTK set up just like before, so let's go ahead and just plug it in. Okay, everything's still working. All right, let's connect to my Wi-Fi again. Okay, it says your Mac is activated. Let's restart and see what happens. And there it is! Yes! We had successfully activated it with the correct serial number and MAC addresses. So let me go ahead and go through the setup, and then we will take a final look at the system. And just like that, we're in. So let's go ahead and take a look at About This Mac. So yep, you can see that serial number that we programmed in is right there. Apple Development Platform, A12Z Bionic, 16 gigs of system memory installed. Go over to storage here, you can see it's just 128 gigs because, well, we only put one 128 gigabyte NAND on it. Let's go into here. A12Z video chipset, of course. And there's the AP0128P SSD. Guess that's what the firmware calls it. And yeah, everything looks really good. 16 gigabytes of LPDDR4. So yeah, I'm very satisfied with that. So the last thing I want to do here is get this whole thing buttoned up in a 2018 Mac Mini chassis, and then we'll have basically a complete system. So let's start getting that put together, and then we'll take a look at the final system. All right, as you can see here, I've got a Mac Mini chassis out, a 2018 Mac Mini chassis. And let's just first go ahead and test fit the board. And I want to show you something that I noticed with this. So we'll go ahead and put the board in. Now, as you can see, I've got the board in there. And one interesting thing you might notice is this connector right here. So what this connector is for on the 2018 Mac Mini chassis is this little power LED located right here on the front. And what I found interesting is the DTK logic board actually has pads for that connector right there. But in a normal DTK chassis, this is the connector that's used for the front LED. And the reason they use this connector is because on the DTK and even on the M1 Mac Mini and stuff like that, the LED has actually two LEDs in it. It has one white LED for the normal power LED, and it also has an amber LED that's used to indicate if the machine's in DFU mode, recovery mode, or what have you. Now, of course, the 2018 Mac Mini doesn't have that, so it just uses this standard 2-pin connector here to connect to the logic board. Now, I have tested this on another one of these DTK boards before, and this connector does indeed allow you to use the 2018 Mac Mini style power LED with the DTK logic board. And I found that really, really cool because now that is possible, I can literally just connect the power LED like any normal Mac Mini and it'll work just like I'd expect it to. So when I originally did this, I was thinking that I wasn't going to be able to use the power LED on the front of the case here, but that actually turns out not to be the case, luckily enough. So I'm going to get this DTK board back up on the preheater. I've actually got a bunch of these little 2-pin connectors, these Molex Pico Easy Mate connectors is what they're called. So we're going to go ahead and just solder one on here. That way I can just plug this in and have the power LED work like a normal Mac Mini. Alright, so as you can see, I've got the DTK board back up on the board preheater here. So the first thing we're going to do is just clear off all of this lead-free solder on these pads. That way it'll make it a lot easier to solder the new connector on without actually melting it. So just start by applying some flux. Then we'll apply some leaded solder. Then we'll wick the pads. And lastly, we'll apply yet again some fresh leaded solder. Clean up some of the flux. Just add a little bit there. And now I'll go ahead and turn my hot air on and get that warming up, and then we can just heat the connector to solder it onto the board. Alright, so I've got a brand new connector out here. And we'll just get it into position. And then just heat it to solder it onto the board. Okay, and that looks really good there, so we're just going to take some more rubbing alcohol and remove the rest of that flux there, and then that should be all done. Alright, so as you can see, I've got the board back out, and I've got all the parts here to assemble it into a working and fully complete DTK Mac Mini, I guess you could say. So right here, I've got an I/O plate for an M1 Mac Mini. So that's the first thing we need to install, because obviously this has to run underneath the heatsink. And then I've also got a DTK heatsink right here. You can see it's got that weird goopy black thermal paste on it already. So we simply need to, screw it down on top of the SoC there. So the first thing, like I said, is we need to run these antenna cables. So first we're going to just put this in position, just like so, and then we're going to take this antenna and just run it through here. Okay, so there we go, we've got our antennas connected. So now we just need to put the heatsink on, and that kind of just goes in like that. And we'll flip the board over and align the screw holes on the bottom. Alright, and that's the heatsink fully installed. So now we can fully put on this I/O plate here. Okay, and now that that's on, we can get a couple screws for it in position. And we can plug in the power button ribbon. And as you can see, that connector is a little bit broken, but you don't really need that retention flap on these style connectors anyway. This will still work with no problem at all. And the last thing we need to install is the speaker. Okay, so that's looking really good there. We've got everything connected on the front I/O. We've got it mostly screwed in there. We've got the speaker on, Wi-Fi antennas plugged in. So the last thing we need to do is get this board assembly installed into the 2018 Mac Mini chassis. Now, one thing you might notice now that I've put that in there is that none of these screw holes actually line up to any of the screws in the 2018 chassis. Now, that's probably something I'd expect in this case because, well, the 2018 board is slightly different than this, of course. But it's still held in pretty well with just the clips on the front panel here, or the I/O panel here. So I'm not really worried about that at all. So let's go ahead and plug the power supply cable in. Just like that. We'll plug in our power LED connector that we just soldered on. There we go. So we got that connector plugged in, and now all we need to do is put the bottom case on here, and that'll be it. We'll have a complete system. Oh, and of course the fan as well. Actually, let's go ahead and get that in as well. So the fan, this is just a normal 2018 Mac Mini fan. That just plugs in here. And once it's aligned, it just has 4 screws that hold it in. And there we go, the fan is nice and secured to the heatsink here, as well as the board itself. So now we just need the bottom case, and it screws, and then that'll be complete. Alright, so I've got those screws out here. First thing we'll do is plug in the last Wi-Fi antenna here. Now I don't have any extras of these screws, so that's just going to have to not be screwed in. No big deal. And we want to make sure that this goes on the right way. It should go on like this, so we need the big screw here. And now we can just put this on. And just like that, we've got a complete DTK. Now that is a really cool sight to see here. So, the last thing we need to do is get this hooked up to a keyboard, monitor, and mouse once again, give it a final test, and we can take a look at the full DTK up and running. Alright, so as you can see here, I've gotten the DTK fully reassembled, got it hooked up to the keyboard, monitor, and mouse. So with everything all ready to go, let's go ahead and power it on and take a look at the final results. You can see the power LED on the front is functioning as expected. And it has fully booted into macOS. And if I feel on the back here, the fan is indeed working. On these DTKs, the fan just runs at a constant speed at all times. It seems to be about half the max speed of what this fan can run at based on what I've heard on other Mac Minis. But let's go ahead and log in and take a look at the system specs. Alright, so as you can see, we're booted up into a copy of macOS Big Sur version 11.2.3, which, as I mentioned before, is the latest version of macOS that actually can natively run on the DTK. So we did take a look at this earlier, but there are the basic specs and system profiler here. And yeah, everything seems to be working just fine. We have a full Wi-Fi connection here. And that has been basically the full restoration of this A12Z based Apple Developer Transition Kit. Now, as I mentioned before, this is something I've wanted for a very long time, so the fact that I have a fully complete system in a working chassis with every functional item working as expected on the device, that is definitely very cool. So with that, I hope you enjoyed this video.